Hi guys! Well, here we are, part 3 of our summer assignment, also known as Baby Chem Boot Camp. So again, we're just going to be doing review materials from Chemistry 1. Today we're going to take a look at stoichiometry, which I know some students love and some students hate. Well, summertime is a good time to refresh those stoichiometry memories, right? All right, so let's get started. Okay, so stoichiometry is basically dimensional analysis or conversions. The difference from a regular conversion, like converting how old I am in years to how old I am in seconds, which we're not going to do right now, that wouldn't be pretty, is that we're converting from reactants to products, or vice versa. But usually we're using it in that we want to know how much we need to start with in order to get the amount of product we need, or we know how much starting material we have and we want to analyze how much product we're going to end up with. That's usually why we're doing stoichiometry. And that's true in class, in research, in industry. So AP Chem, step 1 in AP Chem, always, actually in chemistry, not just AP Chem, in chemistry, is to write a good, balanced chemical equation. Now in Chem 1, we are very often given the equation, and the biggest thing we have to do is balance it. In honors chemistry, you were given reactants and had to predict products. You were given reactants in words, and you had to convert that to formulas and then predict products, things like that. In AP Chem, you will definitely be given the chemical reactions as words and have to convert them to formulas, to a chemical equation, and balance it. But the step 1 in chemistry is to make sure you have that balanced equation so that you know your ratios of what you're doing. So let's just do some review here. Oh, I'm gonna get out my drawing materials. Ooh, yellow. I don't want yellow. Okay, so I don't want blue either. I have a blue background. Let's go with red. Okay, so remember that sides are balanced, which means that we want the same number of atoms on our reactant side as our product side when we're balancing an equation. So it's like this arrow is an equal sign. So here we see that we have 2 carbons, and here we have 2 carbons. Here we have 5 hydrogens plus this hydrogen for a total of 6 hydrogens. So we need to make sure we have 6 hydrogens over here, which we do because we have 3 times 2 for a total of 6 hydrogens. And here we have 1 oxygen over here. And here we have 3 times 2, 6 oxygens. So 6 plus 1 equals 7. Pretty easy there, right? So we need 7 oxygens on this side. Well, here we have 2 times 2. So that's 4 oxygens. Plus, we have 3 times 1 there for 3 oxygens. So 4 plus 3 equals 7 oxygens. So this guy is balanced. We also, in chemistry, in Chem 1 in honors chemistry, we might not have been as strict about it, but now we are. States of matter. So liquid, gas, remember that we have aqueous, that means it's a solid dissolved in water. Of course, solids, we got to have those states of matter in there because we're going to be using a lot of formulas and rules of chemistry where it matters what the state of matter is. And we can add conditions over the arrow, right? So I put this little equal sign here. I'm going to grab my eraser. We could write other things here, right? We could write change. We could write catalyst, like sunlight can be a catalyst. We can write all sorts of things, heat, all kinds of things. So we put over the arrow things that are affecting the equation without being part of the actual chemical reaction. So that's why we put catalyst there. All right. We need to remember our types of chemical reactions. I really like this chart. Down at the bottom, I put the reference there so that you can go directly to this if you want to get a bigger size. It's also in the outline of this unit. So synthesis, remember we have two separate elements combining together to make one. Decomposition, we have a compound that's breaking apart into its separate elements. Single displacement, we have two elements that are bonded together and one element that's by itself. That one that's by itself is more reactive. And we'll talk about reaction series more during the year. So that more reactive element is going to bump off the other element and make a new compound, leaving that other guy by itself. I make the example here in class. I have two analogies that I make. One, this is like there's a couple and they break up and one of them starts dating one of their friends and the ex is hanging out by themselves. Another analogy for this is like you wake up in the morning and you go to get dressed and you pick out a shirt and you put your shirt on and you go, no, I don't like that shirt. So you take off the shirt and put on a different shirt. You being B and A and C being the different shirts. Whereas double displacement is like you put on your favorite shirt, your best friend puts on their favorite shirt, you meet up and you go, wow, I really like your shirt. He or she says, I really like your shirt, and you switch shirts. So in double displacement, B and D would be the people, and A and C would be the shirts, and so the people switch shirts. Combustion, a complete combustion, we're going to have a hydrocarbon. We know there's lots of different hydrocarbons. That means that there's a carbon with hydrogens bonded to it. You can have other things attached to that hydrocarbon, like an alcohol, an OH. It's got to be in the presence of oxygen. Keep in mind, stop, drop, and roll, right? We stop, drop, and roll so that we suffocate fire so that there's no oxygen there. And that's going to produce carbon dioxide, water, and a source of energy. We usually associate heat and light with combustion. And in incomplete combustion, we have the same reactions, but we also have carbon monoxide and carbon. So a great example of this is burning coal, right? We get carbon monoxide. You can think of a furnace. We've got to have carbon monoxide detectors around a furnace because it also produces carbon monoxide and carbon or soot, ash, right? So we have that too. So I really like this visual because not only does it give the neutral examples that we use, like A plus B equals AB results in AB, but it gives an actual chemical example. And then down here we have that reactivity series, which means that we can predict what's going to happen in those single and double displacements, right? So we see here potassium is more reactive than nickel. So if nickel is bonded to an anion and comes in contact with potassium, potassium is going to displace that nickel and bond to that hydrogen. But if it's reversed, potassium's bonded to, let's say, fluorine, and nickel comes along. Nickel is not reactive enough to displace that potassium. So reactive series are important, because just because you bring things together doesn't mean they're going to react. And we will talk more about the reactivity series in class when we talk about, that will actually be in our first unit when we talk about periodic trends more. Okay, percent composition. You know, like any percentage or ratio, it's the part over the whole. So if we want to know the percent of an element in a compound, we're going to take the mass of the element in the compound over the total mass of the compound. And of course, to get a percentage, we times by 100. So here we have an example. We want to know how much iron there is in iron 3 oxide. So we take the total mass of iron, which there are 2 iron atoms there, over the total mass of iron 3 oxide, times it by 100, and we see that iron makes up 70% of iron 3 oxide. So if you want to do a quick practice now, you can pause this and find the percent of hydrogen within methane. Should be pretty quick. Okay, so if you gave that one a try, hydrogen weighs 1. There are 4 of them, so our total mass there is 4 for hydrogen. Carbon weighs 12, so 12 plus those 4 hydrogens is 16. So hydrogen makes up 25% of methane, which is CH4. All right, moving on. So this brings us to our atomic masses. Remember, atoms are really small. And actually, when we talk about the mass of one atom, we use atomic mass units, or AMUs. The entire periodic table, the weight of an AMU of one atom is based on carbon 12. So we base that on the 12th of the mass of carbon 12. This gives us a basis of comparison for all other atoms. And when we talk about weights directly off the periodic table, we're actually talking about AMUs, because everything on the periodic table represents one atom in that element. So elements occur in nature as a mixture of isotopes. Ooh, real quick. What's an isotope? Quick review. Reminder that an isotope is same element with a different number, oops, gotta get an I in there, of what? Neutrons, right? So protons and neutrons are what give an atom mass. So if it's the same element, we have the same number of protons. But if we have a different number of neutrons, then we are going to have a different mass. So here we see, excuse me, when we look at copper, when we take a sample of copper out in nature, 69.09% of that copper will weigh 63 AMU, and 30.91% will weigh 65 AMU, and here we see a very nice chart of that. So the average atomic mass of copper is 63 6.55 AMU. How do we get that? Remember, we take the mass, so here we're going to take 63, and we multiply it by the percent that it is abundant. We do that for all of the isotopes present. And then we add up those results. So we have 63 times 0.6909 and 65 plus 65 times 0.3091, and that is going to give us 63.55 AMU. So molar mass, getting into grams now, is the mass of, so molar mass, you might remember, is going to be the mass in 1 mole, right? Thank you, Avogadro, for coming up with this guy, right? So remember that 1 mole equals 6.02 times 10 to the 23rd units. We're going to use units because we can do formula units, molecules, compounds, particles, atoms, right? Like there's a whole bunch of things we can use that for. 6.02 times to the 23rd eggs is 1 mole of eggs, right? It doesn't matter what we're talking about. And that is going to equal the molar mass. So on the periodic table, that mass, like when we talk about 1 carbon atom, that weighs 12 AMU. But when we talk about 1 mole of carbon, 1 carbon mole, that equals 12 grams per mole. And make sure you write out those units, right? In Chem 1, we let you guys get away with a little bit more. Important to get all those units now. All right, so now that brings us to our stoichiometry. So the mole bridge, okay? We can have liters, we can have particles or formula units or molecules, right? That's that whole guy, or we can have grams. So for liters, this is going to be a gas, and this is volume. Particles can be anything, and that's an amount, right? And grams can be anything, and of course this is mass. So when we're given a mass, we are going to use the molar mass to get to moles. When we're given particles, we're going to use Avogadro's number to get to moles. And when we're given a volume of a gas, we're going to use 22.7 liters at STP to get to moles. Now remember, STP is standard temperature and pressure. If we're not at standard temperature and pressure, we're going to have to use gas law, PV equals nRT, to figure out our moles. We will talk about that more in the year. I just want you to kind of have like a little thought bubble here, okay, in your notes. Just kind of keep in mind that we might have to bring in PV nRT for this guy if we don't have STP. We will apply that. Okay. All right. Then once we're in moles of A, our known moles, we can go to moles of B. Now this can be reactants to products, from one reactant to another reactant. Like, hey, I know that I have, 700 grams of methane gas. I want to know how much oxygen do I need to supply to burn that methane gas, so that would be reactant to reactant. We can have 700 grams down here. We would be here, 700 grams of methane gas, and I want to know how much carbon dioxide that will produce. So I would convert to moles, convert to carbon dioxide moles using that balanced chemical equation. And then if we're at STP, I can go to liters of carbon dioxide, or I can go to a weight of carbon dioxide. So it just shows us this is our starting spot. We got to get to moles of one thing. Then here is where we use our balanced chemical equation. That's why that guy is so important that we talked about at the beginning of the lecture. And then we can get to where we're going to figure out the unknown. So this is huge, okay? Got to do this first. This is step one, always, balancing that chemical equation. Can't emphasize that enough. Although right now you're probably thinking, you have emphasized that enough. All right, formulas, okay. We have two types of formulas, right? We have the molecular formula and we have the empirical formula. The molecular formula is what the molecule actually is, and the empirical formula is the reduced value of the molecular formula. So here we're looking at, looks like C6H6, of course, can be reduced to CH. So for empirical formula, remember we change percentages into grams because a percent is out of 100. So we just pretend that that percent is out of 100 grams. So if we say carbon is 39% of the molecule, then we're going to pretend we have 39 grams of carbon. And then we convert that to moles. We divide everything present by the smallest number of moles to get a ratio, and that's going to become our formula, because remember that these numbers down here, these subscripts, are ratios. We're saying that we have 6 carbons to every 6 hydrogens. And that is determined by mass. So that's what this guy does. And we will practice that in this lecture. Empirical to molecular formula, right. So the empirical is the lowest ratio. The molecular is how the molecule actually exists, and we need the molar mass. So we take the mass of the actual molecule, divide the mass of the empirical formula into the molecular mass. That tells us how many times to multiply it out, and then we add that through our entire formula. Again, we will practice this. Limiting reagent. So a limiting reagent or reactant is the reactant we're going to completely use up, and all our other reactants will be in excess. The limiting reagent is what will determine how much product we end up with. So as some of you know, my favorite analogy is to use s'mores, right? We know that the formula for a s'more, we need 2 graham crackers plus 1 marshmallow plus, I like a lot of chocolate, and I'm going to say 3 chocolate pieces will result in 1 s'more, which is written like this. There you go. That is the balanced chemical equation for s'more making, in case you were wondering. So let's say I have 5 boxes of graham crackers and I have 100 chocolate pieces, but I have 2 marshmallows. How many s'mores can I make? I can make 2 s'mores because marshmallows are my limiting reactant or ingredient. I can only make as many s'mores as those marshmallows are. And the other 2 guys are going to be in excess. We'll have extra graham crackers and extra chocolate pieces. Doesn't mean we can't eat those graham crackers and chocolate pieces, but it means we can't make s'mores. You have 2 marshmallows, you can only make 2 s'mores. All right, I'm not going to read through this. Basically, you're doing the stoichiometry twice and comparing whichever is the smallest amount of product you can make is going to be your limiting reactant and going to determine the amount of product you use or you produce, and it determines how much of the other reactants you use up. We will practice this in just a minute. Yield, percent yield, is taking what you actually produce. Remember, yield is the same as saying like production, how much you produce. And so to get our percentage, we're going to do part over the whole. So actual means what you got produced in the lab. So the lab is the actual yield. And theoretical is your calculations. Product calculated is theoretical yield. So you want your lab amount, your lab yield over your theoretical yield. The analogy that I use in Chem 1 is like baking cupcakes, right? If you look at the back of a cupcake mix or a cupcake recipe, it usually says that it will yield 24 cupcakes or 2 dozen cupcakes. I like my cupcakes to be big. I don't like them to be little. And so I only yield 21 or 22 cupcakes when I make cupcakes. So my percent yield, let's say I get 21 is what I actually make because I like to fill those little cupcake liners up. I was supposed to get 24, multiply that by 100. Let's see, what's my percent yield when I make cupcakes? 21 divided by 24. My percent yield is 87.5. Got to go to sig fig, so that would be 88% yield. So there you go. All right, time for us to do some practice. That's the end of our notes there, and the rest of these slides are practice. So take a look at this, give it a try, come back for the answer. Okay, so here we've taken the abundance and changed it to an actual number from our percentages. So we're moving all these decimals over here, and we're multiplying the masses by their abundances, adding them up. And so we get an average atomic mass right here following our sig figs. We've got 6 sig figs, so we're going to keep that in our answer. And when we look back at the periodic table, we see that this correlates with neon. All right, let's go to our next problem. We've got another practice. Pause and take a look. Okay, let's take a look at this one. This is a little harder. This is more along our lines of an AP Chem type average atomic mass problem. So this is how we would set it up normally with our formula, but we see that we have 2 variables here. We don't know the abundance of both isotopes. So what we do is we take the average atomic mass and we subtract the mass of the isotope that is closest to that, because that's the one that's going to take up, be the most abundant. And so we see the difference between these two is this guy right here. And so the difference between those two is going to go to our least abundant isotope. And so we take the mass of the least abundant isotope times it by that difference. And then we take the mass of the most abundant isotope and we times it by the difference between 100 and how prevalent that lesser abundant isotope is. So these two numbers together should equal 100. And if we had 3 isotopes, then they should all equal 100, right? Because the abundance would be 100% of the isotopes in existence. And so that gives us, we solve for 238 there. All right, let's take a look at our next one. We've got a Chem 1 type problem. Take a look, give it a try, and come back. So we see here that we have 59.9% titanium. The first thing we want to do is take that percentage and pretend that it's grams, right? Because a percentage is out of 100, so we're going to pretend that this is out of 100 grams. So we're going to say that we have 59.9 grams of titanium. We're going to convert that to moles using the molar mass of titanium, and we get 1.26 moles of titanium. How much oxygen do we have? Well, remember that the amount of oxygen is out of 100. So we're going to take 100 minus the amount of titanium, and that means that we have 41.1 grams of oxygen. We convert that to moles, and we get 2.57 moles of oxygen. So we're going to divide both of these by whichever one is smallest, which is 1.26. So here we get 1. And here we get 2. So our empirical formula is TiO2. Our ratio is a 1 to 2. Let's look at our next problem where we are going to figure out our molecular formula. So give it a try. Okay, so here they're giving us straight masses, so we don't need to do our thing where we pretend that a percentage is a mass. And we take both of these and we convert them to moles using molar masses. So we have that here. And then we're going to divide both by whichever one is the smallest. So we get that, and we get this. And so we see that our empirical formula is NO2. Now we want to know what our molecular formula is. They're telling us that the molecular mass is 92 grams per mole. So what we do is we take our empirical formula and we find out our empirical molar mass, which would be, I've already written it down, so I'm going to look over here, 45.98 grams per mole. Notice that I'm writing out my units everywhere, and including my elements and everything. Show my work. Okay, so now we're going to take 92 and we're going to divide it by 45.98. Hopefully it's already obvious that that's going to be 2. So then we can take this information, and so our molecular formula is going to be N2O4, because we multiply everything in the formula by 2. So this is our empirical formula and weight, and this is our molecular formula, and they gave us the weight right there. Next problem, AP Chem style molecular formula. So this one is a little harder. I was thinking if I was going to give you any hints. Take a look and we'll come back. All right, so hopefully you did a little thinking here. So a basic hydrocarbon is basically, trying to think how I want to word this. We know that we're going to have a carbon with two hydrogens. And so that's going to be 14 grams. Okay. How we come up with this is that if you think about a carbon, right, can have four hydrogens off of it, but we don't always know what it's bonding with, right? Is it bonding with another carbon? Does it have a double bond? Things like that. And so we base it on CH2 as 14 grams. You might not have known that, and that's okay. Now that you know that, you can use this as your empirical formula and mass. And so we know we're going to divide 14 grams into 28 grams, so that means ethylene is times 2. Cyclobutene, when we do 14 into 56, that's going to be times 3. Pentene, 14 into 70 is times 5. And cyclohexane into 84 is times 6. So now we can figure out these formulas based on that CH2. So that means that ethylene is going to be C2H4, and cyclobutene is going to be C3H6, and pentene is going to be C5H10, and cyclohexane is going to be C6H12. And if you want to see how those look, this guy has a double bond with the hydrogens like this. This guy, cyclobutane, I'm sorry, that's times 4, isn't it? See? I make mistakes too. That's going to be times 4. So this is going to be 4 and 8, right? Butene. Okay, and so we've got, it's going to be this shape, like this with a double bond. So each one of these points is a carbon, and we've got a double bond here. So carbon, 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 carbon. And so each one of these is going to have 2 bonds, and this is going to have this is going to have 1 hydrogen and 1 hydrogen right there. And here we have, it's just going to be a straight chain like this. So each one of the points is a carbon. And this guy is going to be shaped like that with 6. And each one of these is going to be a hydrogen sticking off of there. So this is organic chemistry because we have a carbon backbone chain. You have not learned a lot of organic yet, so we will talk about that during the year. Organic chemistry is actually not on the AP exam or the College Board program of studies, but of course we will talk about it because it's part of chemistry. All right, some Chem 1 stoichiometry. Give this a try. While you're trying this, I'm going to move inside because it's really hot now. Hey, oh, that's better. Now I'm inside in the air conditioning. See, summer assignment during the summer. Okay, so we were looking at this problem, these two problems. This first one is more of the Chem 1-1, and this is a little bit more progressive. Not entirely an AP level, but a little more aggressive. All right, so let's take a look here. So the first thing we had to do was we had to balance, right? We needed 2 aluminums and 2 irons to get this equation balanced. They gave us the 15 grams of iron. Using the molar mass, we converted that to moles of iron. And then we were trying to get from iron to the amount of iron 3 oxide. And so we need to use our mole ratio from our equation. So we get our 2 moles from our equation and 1 mole there, right? There's the 2, there's the 1 mole. And now we're in moles of iron 3 oxide. We need to convert that to grams. So we have the molecular mass of iron 3 oxide. And there's our answer right there. I don't like the sig figs on that one. So really it should be 21 grams of Fe2O3 because we're given 2 sig figs in our original measurement. All right, let's go to our second problem here. Drawing a line. Oops, moved my whole gig over here. All right, oops. There we go, back over. Okay, so first off, we are taking a piece of aluminum foil, which is pure aluminum, and dissolving it into some hydrochloric acid. And we know that that is, so this is solid, this is liquid, and we know that we're producing some hydrogen gas because it's telling us so. And we're also going to produce some aqueous aluminum chloride. And we know that aluminum chloride is AlCl3. By doing our swap and drop, aluminum has a +3 charge, chlorine a -1, and then we need to balance our equation. How do we get 27.82 grams? Well, they give us the size of that aluminum foil. So you need to figure out the volume there by multiplying the height times the width times the length. And then they also give us the density. So we've got a density of grams per centimeter cubed, and we've got a volume of 10.3 centimeters cubed by multiplying those measurements. And so that's going to give us that 27.82 grams of aluminum. So that's how we get this number here. And then we need to convert that to moles. We do our mole ratio of aluminum to hydrogen gas by using our balanced equation up there. And then we convert from moles of hydrogen gas to grams of hydrogen gas, and that gives us an answer of 3.1 grams of hydrogen. I was just checking my sig figs, and I'm missing a sig fig there. You think it should be a 0. So there we go on that one. A little bit harder there because you got a couple of different things you need to do. Here you have some descriptions of chemical reactions that are happening. Write the formulas and balance them. You see that I have removed one. Don't do that one. All right, pause, give it a go, and come on back. Okay, here are the answers to those chemical equations. I did include the one that I eliminated just in case you felt a need to do that one. The reason that it's not a Chem 1 problem is because it has an intermediate step, which not all Chem 1 students have talked about intermediate steps. Hopefully you've thought about that not all chemical reactions are just reactant and automatically go to a product. Sometimes they react and create a product, and then those products react and so on. Actually, baking soda and vinegar is one of these types of reactions. It just doesn't go from one thing to another one. There's actually intermediate steps in between, and we'll be talking about that during the year. So I did include this so that you can see how ammonia reacts to oxygen and it produces water, and nitrogen monoxide, ammonium, and then water and nitrogen monoxide. And then our final one there. All right, let's look at our next problem, little limiting reactant practice. So we're going to have some stoichiometry and then compare your products to find out how much unreacted material remains. An important part of chemistry is making sure you know what question is actually being answered and that you answer it. So our first step was to come up with our balanced chemical equation, which we see here. And then we took our starting amounts and of each reactant and converted them to moles, and then used our mole ratios from the balanced chemical equation to come up with how many moles of our product we were creating. So the nitrogen produces about 7 moles of ammonium, and the hydrogen gas given produces 167 moles. And so our limiting reagent is going to be that nitrogen. So we take the amount of product that we're actually going to produce. And I wrote this wrong here. Let's change that. It's not nitrogen gas. It's actually our product. So this should be NH3. So this is how many moles we're going to produce. And now we're going to convert that from our ratio equivalents in the balanced chemical equation to moles of hydrogen that we need, and then convert that to grams. And so we're actually going to use about 21.4 grams of hydrogen gas. Well, we have 500, so when we subtract out how much we use, we end up with 478.52 grams that are wasted, that we didn't need to add into this reaction. So this is why limiting reagent is so important, because in industry and in research, we don't want to waste. This is a horrible amount of waste. And that's going to decrease your profit margins. That's going to waste your grant money that you've worked so hard to get for your research, all sorts of things. And some reactants that we use are hard to get. So we never want to waste our reactants. All right, here we go. Here's a % yield practice, Chem 1 level. Pause and give it a try. Okay, so the first thing we did was we write our balanced chemical reactions. So we have aluminum burning in bromine. Remember that bromine is a diatom, so we need 2 of them producing aluminum bromide. And we balance that equation. In a laboratory, 6 grams of aluminum reacts with excess bromine. So we know that we're going to use the amount of aluminum to do our stoichiometry. And we end up with a theoretical yield, because we used our calculations, to get 59.3 grams of aluminum bromide. When we're in the lab, we actually produce 50.3 grams. So our % yield part over the whole is 84.8%. Not bad. A little bit of waste, but not too bad. All right, try an AP Chem level % yield question. Okay, so the first thing we need to do is figure out our limiting reagent, which here we see is the mercury. And so the mercury that we have is going to produce 0.0498 moles of mercury bromide. So we're going to take that amount is our theoretical yield. And we're told that we can only have a % yield of 74%. So we're going to bring down our theoretical yield and put it on the bottom. Our actual yield is our variable that we're looking for, and that is going to give us a % yield of 0.743. And so we take this and we solve for x, and x is 0.037 moles. So this is our actual yield in the lab. And we convert that to grams so that we know how much mercury bromide we're actually going to produce, and we see that right here. If we have 0% air, we're going to take our actual moles from right here and calculate out how much bromine is needed, which is 5.93 grams is needed. We're putting in 9. So when we subtract out what we used, we're going to have an excess or a wasted amount of 3.07 grams. All right, our last problem here, bringing it all together. Last problem, give it a try. Okay, here we are. we had a whole bunch of stuff that we brought together in this problem. So let's take a look. So first off, we wrote our chemical reaction. We have a hydrocarbon that is in the presence of oxygen, combusting and producing carbon dioxide and water. We know that we have 10.68 grams of that hydrocarbon, and we know that we have basically 16 grams of carbon dioxide and 4.3 grams of water. We know that mass can neither be created nor destroyed, so the total mass of our products has to equal the total mass of our reactants. So we know the masses of our carbon dioxide and our water. So we bring it down here and we find out that carbon by mass makes up 27% of our carbon dioxide, and hydrogen makes up 11% of our water. So we know that the carbon and hydrogen in our hydrocarbons has to be, and our reactant has to be the same grams, the same mass that we are producing. So when we take the mass of the carbon dioxide and we multiply it by the percent that is carbon, we find out that in our products we have 4.36 grams of carbon. So on our product side, we have produced 4.36 grams of carbon. And by taking the mass of the water and knowing that that water is at 11% hydrogen, we know that we have produced 0.486 grams of hydrogen. So that means that these masses have to also be in our reactants. So we know that that hydrocarbon weighs 10.68 here. I'm actually going to change colors. So we subtract out the mass of the carbons, we subtract out the mass of the hydrogen, and what's left is our mass of oxygen. So we now know that we have 5.834 grams that are going to be oxygen in this hydrocarbon. This oxygen here, we don't actually care about because we could just subtract out 10.68 and we would know the rest goes with that, but that we're not actually solving for that. Okay, then we come over here and now we know we calculated the mass of carbon, the mass of hydrogen, and the mass of oxygen. So now we do that thing where we do the percent of mass out of the whole thing. So here we get, when we do this, we get 40% of our hydrocarbon is carbon, and 4.5% is hydrogen, and 54.6% is oxygen. Then remember, to figure out our ratios, we pretend that that percentage is grams because it's out of 100, right? So we do this little thing and we're pretending that these are all grams now. And we convert them to moles. So these are our molar masses and we're figuring out how many moles of carbon we have. So in that hydrocarbon, we have 3.3 moles of carbon, 4.5 moles of hydrogen, and 3.4 moles of oxygen. We then divide by the smallest one, which is 3.3, and we get 1 carbon, 1.3 hydrogens, and 1 oxygen. Well, these are not whole numbers, so we multiply out till we get to a whole number, which this guy, the hydrogen needs to be multiplied by 3 to get to a whole number. So our carbon then becomes 3, this becomes basically 4, and this becomes 3. So our empirical formula is C3H4O3 with an empirical mass of 88 grams per mole. And I'm sorry, I didn't write the units there. All right, well, we were told that our molecular formula our molecular mass is 176 grams per mole. If our empirical formula is 88 grams per mole, we divide the empirical mass into the molecular mass, and we see that it is double. So we multiply everything in our empirical formula by 2, and we get C6H8O6, and that is our molecular formula, which if we back check should add up to 176 grams per mole. So you can see in this last problem, we brought a lot of things together that we learned in Baby Chem Boot Camp. So hopefully this is a good foundation for you going into AP Chemistry. If you have any questions, email me and look at the supplemental material that I'm posting along with these videos. All right, go enjoy some summer.